From today onwards, we shall start discussing bulk crystal growth, and you know that so far as the bulk crystal growth is concerned, there are other type of crystal growth which is known as the epitaxial crystal growth. Bulk crystal growth, another is the epitaxial crystal growth. There are two types of crystal growth that we shall discuss in this class. Okay. Now, in bulk crystal growth, mainly we shall concentrate our discussion on silicon and gallium arsenide. In bulk crystal growth, we shall concentrate our discussion on silicon and gallium arsenide. Why? Because these are the two most important semiconductors which are used for the fabrication of semiconductor devices, and you know that silicon is the most important material. We have discussed this thing in our earlier class. Now, so far as the whole electronic material is concerned, particularly the IC technology, silicon is the only material. But if you go for the optoelectronic materials or the high speed material for application in high speed or high mobility area, then only these 3-5 semiconductors or gallium arsenide is used. So, today we shall concentrate our discussion on the silicon crystal growth. Now, if you see this view graph, you will see that first we start from a material which is the starting material, and then polycrystalline semiconductor will be grown, and finally to the single crystal, and then single crystal will be cut into pieces to form the wafer on which the whole technology is based on. And for silicon, you see that we start from SiO2 and then we shall make some distillation and reduction to obtain the metallurgical grade silicon and finally to semiconductor grade or electronic grade silicon, and then there will be crystal growth. Then the crystal will be grinded, saw, polished, etc., to obtain the wafer. For gallium arsenide, what we shall do? We shall use gallium and arsenic, then we synthesis gallium arsenide, finally the crystal growth will be done and the same process will be followed to obtain the wafer. Now, for silicon crystal growth, you see that there are two basic and very important technologies involved in the silicon crystal growth. One is the manufacturing technology of high purity raw material. That is very important. You see that this high purity raw material, first is the this is the precondition that you cannot grow silicon using just SiO2 or sand taking from the earth crust, that is not possible. So, first you have to take the SiO2 that is silica or the quartzite SiO2, then you have to make some kind of processing to obtain the very high purity grade of silicon material. And so, if you consider that first that the manufacturing technology of high purity raw material will be taken care of, and then the second part is the dislocation free crystal growth technology. Remember that dislocation free crystal growth technology, right. So, there are two steps, we shall discuss in detail this both the steps. One is the high purity raw material, another is the dislocation free crystal growth. And when we talk about this high purity raw material, obviously for silicon crystal growth, the high purity raw material, what is the raw material for silicon crystal growth? For silicon crystal growth? Yes, but finally the raw material is silicon. Finally, the raw material is silicon. And high purity means you see that there are 10 nines, that means 99.99999999%, which is known as the 10N. Such kind of purification is required, very high purity material is required. Better if you can use 11N purity, that means 99 and then after decimal 9 nines. So, such kind of purification is required, and that is possible only for silicon only. There is one technology which is known as the Siemens purification method, SIEMENS, Siemens purification method, and using this Siemens purification method, we shall show you that very high quality and high purity silicon can be obtained from silica or quartzite. Then another question comes that about the diameter of the crystal. Diameter of the crystal is very important. If you see the present day technology of IC fabrication, that means chip fabrication, then what is the length of the technology, what is the gate length, what is the channel length, do you know? It is 7 nanometer. By 2018 it will be 7 nanometer. So, what is 7 nanometer? Let us take one example that almost all the IC chip you know that is based on the transistor or the MOS technology. So, that means you have to grow innumerable numbers of MOS transistor, innumerable number. How many MOS transistors are there? How many transistors are there in an IC chip? Millions of. So, if you see that the chip is of say 1 centimeter by 1 centimeter or even less than or larger than that, then how many transistors are there inside? Millions of transistors are there. Okay. So, that means the physical dimension of one of the transistors must be very, very small. So, in that sense the present day technology uses 7 nanometer, particularly that is one organization which is known as International Technology Roadmap for Semiconductors, which is known as International Technology Roadmap for Semiconductor, ITRS. That is an organization, and according to the prediction made by this International Technology Roadmap of Semiconductors, so far as say let us take one example of DRAM. What is DRAM? You know what is DRAM? Dynamic Random Access Memory. So, memory is very important thing in the IC chip. So, this DRAM, so far as the DRAM is concerned, you will find that memory size per chip, it is 4 gigabit in 2004 and in 2018 it will be 120 gigabit. Okay. So, there is a transition from 4 gigabit to 120 gigabit, it is the memory size per chip. Then if you consider the other specifications, say that clock, what is the clock speed of this computer? 2.8. Right. So, now actually it is 4.2 gigahertz which was predicted for 2004, it will be 53 gigahertz. Right. I am giving you the prediction which was for 2018, and then power consumption. It is from 158 watt to 300 watt. So, if you consider this prediction for 2018, which was done by the International Technology Roadmap for Semiconductors, you will find that the memory size per chip will be increased by manifold, then the clock speed will be increased by manifold, power consumption will be increased by manifold, but the size of the chip will not be reduced. That is not possible. Why it is not possible? Because if you increase the memory size per chip, so the physical dimension of the transistors or the CMOS you cannot reduce by very much. Only some scaling is possible, and that scaling is known, probably the physics students know, that is the channel length. Channel length means the channel length of the MOS. When we talk about this channel length, what is channel length? You see that say this is one material, this is say p type silicon or say n type silicon, p type silicon. One example, I have taken one p type silicon. Then two source and drains are fabricated. This is n, this is n plus or n plus, heavily doped say, right. So, then what is the channel length? Channel length is the length between the source and the drain, but the actual length is smaller than this physical dimension. Why? Because the length is determined by the region between two depletion regions. We shall come into the detailed description of the depletion region. You know that this is n type and this is p type. So, there will be a depletion region. Similarly, this is n type, this is p type. So, there will be some depletion region, and in fact, there may be the final region may be this type of thing or that part of the channel. That is predicted to be 7 nanometer. That is predicted to be 7 nanometer. So, under such a circumstance, we have no other option but to increase the diameter of the wafer, so that many more transistors or the MOS devices you can accommodate. And the prediction is 450 millimeter diameter. The what is its dimension in inch? It is almost 18 inch. It is almost 18 inch. So, 18 inch diameter silicon will be used as per the prediction of the ITRS for 2018 IC technology fabrication. So, that means if you want to reduce the cost or if you want to make the yield to be the same, then you have no other option but to increase the diameter of the silicon crystal. Remember that the whole IC technology depends on the silicon wafer. If the material scientists are unable to provide very good quality, very good diameter silicon wafer for fabrication process, the whole fabrication process will be stalled. So, it entirely depends on the diameter of the silicon wafer that is to be provided to the IC manufacturer. And here the important question comes that this very high diameter silicon wafer 18 inch almost, present day we use 12 inch, 13 inch, 300 millimeter, 350 millimeter, that the present day we use. So, this kind of silicon wafer is required for 2018 fabrication as per the prediction. So, the silicon crystal growth is becoming a very hot subject for the future generation IC manufacturing technology also, because unless you can provide very good type of material. In this case, not only the purification, another thing is that the diameter, not only it will be large, at the same time it will be dislocation free. This is another term which is very important, dislocation free. What is dislocation? That is a kind of defect. When we shall discuss about various kinds of defects, we shall discuss in length what is dislocation, how it looks like, etc. But for our present day discussion, dislocation means it is a kind of defect that you have to avoid. So, if the diameter becomes large, so there is a possibility that there will be dislocation, because you can care for small thing, but if the things becomes larger, you cannot expect that the same care can be taken on the whole material. So, that is the reason that not only you need very high diameter material, very high purity 10 N or 11 N purity, at the same time you need the dislocation free material. Okay. Another important factor so far as the dislocation free is concerned is that now it is 7 nanometer. Which one? The gate length. Okay. Earlier it was greater than 7 nanometer, say almost micron type of thing. And what is the dimension of the defect? Dimension of the defect is also of the order of nanometer. So, that means unless you make the dislocation free, this 7 nanometer thing will be jeopardized.
Sir,
yes.
if there are some dislocations, can we remove it?
No, you cannot remove it. There are some process using which you can avoid that place only. There are some place that there is a process using which you can avoid. Say this is your silicon wafer and there is a dislocation here. So, that can be predicted, that can be determined. So, you cannot at the most you cannot use that place only. So, that the other part of can be used, because ultimately you have to make a large number of pieces, because using a whole wafer say of 400 millimeter dimension, how many chips will be there? There will be hundreds of chips obviously. So, that is not a single chip. So, chips which are being made at those points where dislocation are concerned, you can reject. So, that means if this is your whole material, so this is 1 chip, 2 chip, 3 chip, 100 chips can be processed, and if you find that there is dislocation or defects in some regions, so those chips which are made on that region can be rejected, can be removed at the end process. Okay. But since suppose there are some dislocations here, here throughout the material, then what will happen? Then almost all the chips you have to throw out. So, that is not possible, because you have to make the cost also viable. So, that is why the dislocation fee must be done. So, if you now consider the silicon crystal growth, you see that first you have to use silica. This silica is nothing but SiO2, which is also known as quartzite, This is available in Brazil and China, very good quality silica mineral they produce. So, almost all of the silica material which is used as the starting material for silicon crystal growth comes from the Brazil or China. Then this silica is placed in a furnace. Starting material is sand called quartzite. This is placed in a furnace with various forms of carbon. That means, it can be coal, it can be wood chip, it can be coke, etc. Right. Then there is a reduction reaction. Reduction reaction means SiO2 is there, O you have to remove. So, that means some reduction reaction must be performed, and you see that this is the reduction reaction. So, at the end of this reaction, Si is obtained.
How much the temperature required?
Here the temperature required is almost 1200 1300 degree centigrade, very high temperature is required, or even higher than that. In some books you will find that it is 1700 1800 degree centigrade, right. Normally processing silicon is very difficult also, though the technology is very matured and it is available in the market. Why? Because the melting point of silicon is very high. What is the melting point of silicon? 1410 degree centigrade, very very high temperature. So, anything which you want using silicon, particularly the processing technology, you need very high temperature. So, the silicon is first reduced, silica is first reduced into silicon. This silicon is known as the metallurgical grade silicon, Mg, metallurgical grade silicon. That means, it is 98% pure. it is 98% pure, which is known as the metallurgical grade silicon. Now, from metallurgical grade silicon to semiconductor grade silicon, SG silicon. SG silicon is generally known as the semiconductor grade or electronic grade, EG. In some books you will find that it is known as EG, electronic grade silicon. So, what is the difference in purity from 98% to 10N or 11N purity? This step is very important, metallurgical grade silicon to semiconductor grade silicon, using this purification process, which is known as the Siemens purification. I have mentioned just now Siemens purification, because they have obtained the patent in 1960. You know, there is a company named Siemens and they have this patent of purification. So, they earn huge amount of revenue from the silicon processing also, though they have other kinds of communication system technology etc. in Siemens, but they are very useful in purification of silicon as well. Then what happens for this metallurgical grade silicon? You see that this metallurgical grade silicon is pulverized. What is pulverization? What do you mean by pulverization? Yes, pulverization means grinding, crushing. It is means crushing or grinding the material into almost powder, right? That is known as pulverization. Next, the silicon is pulverized and treated with hydrogen chloride to form trichlorosilane at 300 degrees centigrade. So, if you see this reaction, you see that silicon then react with hydrogen chloride to obtain trichlorosilane. Okay? This trichlorosilane is very important product in the sense that its melting point is just 31.8 degrees centigrade. That means it is almost liquid, and the advantage of using a liquid is that you can distill it. You can distill it. So, by fractional distillation of trichlorosilane, you can remove almost all impurity. So, that is the reason that trichlorosilane is made. So, that is very important step. Okay. The importance of trichlorosilane is twofold. One is that using this chlorine, other impurity, say BCl3, say boron is there, say iron is there, where this boron, iron, these are there in the metallurgical grade silicon. It is 98% means there are 2% impurity in it, more than 2% impurity in it. Okay. So, you have to now concentrate on the removal of that 2% impurity from metallurgical grade silicon to obtain the semiconductor or electronic grade silicon. So, this trichlorosilane, as I informed you, this reaction occurs at 300 degree centigrade, not very high temperature is required, but this trichlorosilane is a liquid at room temperature, because its melting point is 31.8 degree centigrade, and this trichlorosilane can be successive distilled. By fractional distillation of this liquid, you can purify. That is why purification step is there, that you can purify the trichlorosilane into very high purity trichlorosilane. And other types of impurity which are there, that I mentioned, say that can be removed as a chloride compound, because you are making the reaction using hydrogen chloride, HCl. Then this trichlorosilane is decomposed using hydrogen to obtain silicon and HCl. So, this silicon is the semiconductor grade or the electronic grade silicon, having 10N or 11N purity. So, most of the cost is involved in the purification of silicon, that means from silica to semiconductor grade silicon. Yes.
So, what type of impure materials removed during purification?
Whatever kind of impurity is there, there are many kinds of impurity because it is a mineral type of thing. So, almost all kinds of element can be there, iron can be there, cobalt can be there, nickel can be there, boron can be there, aluminum can be there, many kinds of impurities are there. And that is the reason, no, because you see that from 98% to 10N on 11 such processes are involved, that means 2% impurity reduction is necessary also in our case. Whatever be the impurity, that is not our lookout, because you need ultimately 10N or 11N purity. So, we cannot bother about any kind of impurity, be it aluminum, be it iron, it is almost same to us, we have to remove it. Okay. Then the decomposition of this trichlorosilane using hydrogen, you get silicon. So, the first part is over. What was the first part? First part was, you see that manufacturing technology of high purity raw material. Now, we are in a position to get the high purity raw material. Then this high purity raw material will be used for single crystal growth of silicon. There are two processes, one is known as the Sharansky technique. What is the pronunciation? The pronunciation is CHO R H HR AL SKEE. That means this, the pronunciation of this is Sharansky, Sharansky, CHO HRAL RAL SKEE. So, basically he is a scientist from Poland, and who at the age of only 31-32 discovered this technique for the bulk crystal growth, single crystal growth of a material. He was doing something using metal melt, he was melting some metal, and unfortunately his pen and dipped inside that melt. So, when he took his pen out from this melt, he saw that some string type of crystal has been grown. So, that was his final inspiration to get into this Sharansky technique. I shall discuss that thing in detail. So, and you see that this 90% silicon crystals are grown by this technique in industry. Silicon, remember, almost 90% of silicon single crystals are grown by this technique, and silicon required for IC fabrication, because other type of silicon is also required for detector material, etc. So, that is a different story, but for IC fabrication the whole lot of silicon is grown out of Sharansky technique. Remember that this technique is for the growth of single crystal. Why single crystal is required? We have discussed that it must be defect free, dislocation free, and mobility will be high. So, those are the reasons that single crystals material are grown. There are other techniques also for crystal growth. One is say float zone technique, another is say Bridgman technique. The Bridgman technique can be horizontal Bridgman, it can be vertical Bridgman, and we shall see that for gallium arsenide fabrication this Bridgman technique is used, and Sharansky and float zone techniques are used for silicon technology. Okay. Now, if you see the Sharansky crystal puller, that is the Sharansky crystal puller, you see that it has many parts. It has many parts. One part is that there is an graphite susceptor, this is the graphite susceptor, and inside which there is a crucible, silica crucible, and the polycrystalline silicon is kept inside this silica crucible. It is heated, that is why the melt is there. So, inside the silica crucible there will be a melt of polycrystalline silicon. So, apart from this graphite susceptor which house the crucible, you see that there must be a heating arrangement. These dotted are the RF coil, these small circles. RF coils, that means using some RF heat source, radio frequency heat source, you can heat this material. Remember that how much temperature is required? It obviously greater than 1410 degree centigrade, because the melting point of silicon is 1410 degree centigrade. So, if you want to get a melt of silicon, that means it must be greater than 1410 degree centigrade. So, almost 1420 degree centigrade is required, and that is very high temperature. That is why you need a radio frequency type of source, using which it can be heated. And this melt, that means this is the melt of polycrystalline silicon. So, when the material is melted, that means it is no more in the crystalline state. It is basically liquid. It is basically liquid. Then one seed crystal is dipped at the surface of the melt. One seed crystal. What is a seed crystal? A seed crystal is the crystal of the single crystal silicon. So, that means this is your crucible on which there is a melt. You dip one seed crystal at the surface of the melt, then you pull it, then you pull it. So, as you pull it, what you will find? That at the boundary between the solid and the liquid, at the boundary between the solid and the liquid, the temperature difference will be there, because the melt temperature is 1410 or 20, that is the melt temperature. But just above the surface, when you put a seed on the melt, the temperature will be somehow less than 1410 or 20. So, it will crystallize. Because of the temperature gradient, it will crystallize. Then you very slowly pull the seed crystal. See, if you very slowly pull the seed crystal, then the whole silicon single crystal will be gradually grown. And at the same time, what will happen? The melt will be, the quantity of the melt will be reduced, because that is being solidified to obtain the crystal. So, basically this Sharansky crystal puller, that is why the name puller is there. You are pulling the crystal. First the seed was, see this neck, the neck is seed, and there is a seed holder which holds the seed, and it is gradually pulled. First, where is the seed? The seed was at the surface of the melt. Then with time it goes up, and this whole crystal is formed. First the melt was say up to this region, this point. The melt gradually reduces, crystal gradually grows, and this is the diameter of the crystal. It will depend on the pull rate of pulling, and the temperature at the solid liquid interface. That is temperature at the solid liquid interface. So, remember that this is very important consideration, and you can vary those parameters using a computer control system. Say you want pull to be 1 millimeter per hour, 1 millimeter per hour, or even less than that. So, only a computer can control the pull rate, using which you will get only 1 millimeter per hour or 5 millimeter per day, because very slowly you have to pull, otherwise what will happen? There will be defect, otherwise there will be defect. It is very smooth must be there. So, that is known as the Sharansky crystal puller. You are pulling the crystal from the melt. So, it is a melt growth process, growing the crystal out of the melt. First you take the electronic grade or semiconductor grade material, you melt it. Where it will melt? On the crucible. The crucible is made of silica, and on which it will be placed? On a graphite susceptor. On a graphite susceptor the crucible is placed, and you have to heat. Where is the heating element? It is behind the graphite susceptor. It is behind the graphite susceptor. Now, the question comes, why there is argon? You see that argon is there and an arrow is given. Why there will be argon? No.
Cannot oxidize.
Yes. Why? What is the problem with oxidation?
Oh, because silica will be formed.
Because no, not only that. Here you have to drive oxygen away from this whole environment. It is because graphite, when heated in presence of oxygen, it will be damaged. Yes, graphite can be heated, but that heat must be not in presence of oxygen. Yes, graphite is also can withstand very high temperature, but not in presence of oxygen, it will be damaged. Another thing is that unless you control the oxygen in the atmosphere, unless you control the atmosphere oxygen, you must control, otherwise what will happen? The material will be oxidized as well, SiO2 will be formed as you told. Okay. So, that is why argon will be passed through the material environment. That means, this argon will replace oxygen. There is oxygen, so it will replace oxygen, and here there must be an exhaust. Here at the bottom there will be an exhaust through which that argon and SiO gas will be removed. SiO gas will be formed and argon will be there. So, there will be a continuous flow of argon. So, the pressure must be controlled in such a way inside the apparatus that the argon pressure remains constant, because it is continuously removing the SiO gas also. So, basically SiO gas is coming out from the surface of the melt, from the crucible surface SiO gas is evolving, and argon is taking those SiO gas to remove it through the exhaust at the bottom. That is why the pressure and the quantity of argon must be controlled very precisely, and that can be done using computer. There is no computer here, you see that there is no control system, but the whole thing is being controlled by a computer. Process parameters like temperature, then temperature gradient, pool rate, argon pressure, everything will be determined by the computer. So, there will be a computer control system. I have shown you a very simple diagram of crystal puller, and apart from a computer control, there must be a optical window to see the diameter of the crystal. You can see the diameter of the crystal using some, say, optical window means there must be a CCD, charged coupled device, CCD camera must be there, using which you can see how much it has grown. What is the diameter? Is it 100? Say you need 150 and you see that it is 152 or 149, then what we have to do? You have to adjust. You have to adjust some of the process parameters. So, using a computer control, using the computer control system, you can adjust those parameters. There is a loop. So, you can adjust the parameter so as to get the exact diameter of the single crystal. So, it is not so simple as it looks like. There will be optical device, there will be computer control system, and argon pressure will be there, everything. And another thing I have to mention that there is one magnetic field also which is used. There is one magnetic field which is also used here at the crucible. Now, why the magnetic field is used? What is the advantage of using a magnetic field for crystal growth? It is because of three factors. One is that oxygen concentration control, to control the oxygen concentration in the crystal growth process. One thing is to reduce impurity contamination, and number 3 is that here you see at the surface of the melt there will be movement, there will be vibration, because at 1420 degree centigrade there is a liquid having some density. So, what would be the surface? Surface will be vibrating. To reduce that vibration, magnetic field is applied. Why? Because unless you reduce the vibration, it will give rise to defects and dislocation. It will give rise to defect and dislocation. So, you see that the magnetic field is very important. It is one is low oxygen concentration, to maintain low oxygen concentration. Number 2 is reducing impurity, and number 3 is maintaining stability of the melt surface for dislocation free growth. For dislocation free growth. So, these are the 3 points for which we use a magnetic field. One point is maintaining low oxygen concentration. Okay. Now, you can ask me, sir, why it is required? It is required because at this high temperature, oxygen will be coming out from silica. Oxygen will be coming out from silica, because there is no aerial oxygen. You have used argon to remove the oxygen from the system. Then what is the source of oxygen? The source of oxygen is silica, because the crucible is silica. So, from the silica crucible, oxygen will automatically be mixed inside the melt, that you have to control. Otherwise, the material will be oxygen rich. Then the problem will be that the melting point of pure silicon is 1410, but if there is sufficient quantity of oxygen in it, so then the temperature will be different. Even plus minus 0.5 degree centigrade temperature also can jeopardize your growth. The temperature to be maintained is very precise manner, otherwise you cannot control the growth. Such diameter, such dislocation free material you cannot grow. So, the temperature is very important factor, because it will be crystallized at the solid liquid interface. at the solid liquid interface, and the interface temperature control is very, very important. So, that is why oxygen controlling is also very important aspect in bulk crystal growth so far as the Sharansky technique is concerned. So, magnetic field in one way control that oxygen concentration. Number 2 is the impurity concentration. There are many impurities, okay, particularly that impurity which can be attracted by magnetic field, iron, cobalt, nickel, etc. Those are rampant in the material. And third one is the stability of the melt surface for dislocation free growth. Stability, maintaining stability of the melt surface, as I told you that the melt surface will be vehemently vibrate. So, that is why magnetic field will be there. Another important aspect of oxygen is that there is one term in crystal growth which is known as Gatoring, G-E-T-T-E-R-I-N-G. Gatoring is a process which remove the unwanted impurity from the surface to the bulk, that is known as Gatoring. Okay. Say this is a crystal, okay. This is a crystal, this is its surface, this is its surface. So, Gatoring actually drives the unwanted impurity from the surface to the bulk or at the back side. How much thickness is required for the device fabrication? How much? Some 1 micron, 2 micron, 5 micron. So, if you can make clean of the whole surface, say 5 micron or 10 micron, say 100 micron, then your purpose will be solved. Let the impurities be settled at the bottom or at the back side, because how the impurity, if there is an impurity, where it will go? So, people have been trying to drive the impurity away from the bulk surface region, because the whole processing technology will be on the surface, the growth will be on the surface, and only some micron at the from the surface to the bulk we use. The other thing we do not use, other thing is removed, basically it is wasted. So, that is the reason that impurity is driven away from the surface region to the bulk or the back side of the substrate or the wafer. That is done by Gatoring, and oxygen plays an important role in Gatoring the impurity. Why? Say there is oxygen, and that oxygen, it is coming from SiO2. If a controlled manner you can put some oxygen in the material, you can control, then there will be an supersaturated oxygen at the say surface of the material or at the bulk of the material, somewhere in the material there will be a supersaturated oxygen region. That oxygen will grow, when it will grow. So, at some time what will happen? Some stress it will provide. So, the stress will be relieved only if some dislocation or defects are formed in the material, and those defects and dislocation trap the impurity. Those dislocation or defect trap the impurity. When we talk about that Gatoring of impurity, where the impurity will go? The impurity will be trapped or will be taken away by the defect or the dislocation in the material, but not at the surface, away from the surface. But how the dislocation is provided at that point? That is done by oxygen. To relieve the strain of the oxygen, dislocation is formed. and that dislocation will trap the impurity material at that point, so that they cannot move. They are trapped at some point away from the surface or the device region. So, basically the devices are made at denuded zone. Denuded zone. The denuded zone means the zone on which the device is made. Okay? The zone and on which the devices are made. Okay? And this is very important zone for us. Okay? This is very important zone for us, and you see that this Gatoring is done away from the denuded zone, and that is done by oxygen, or you can use other type of Gatoring like implantation of phosphorus at the back. There are other types of thing, but this is very intrinsic process. You are using the oxygen taking from the silicon crucible, controlled by the magnetic field, to grow at some point where they relieve the stress by forming some dislocation inside the material, and that dislocation lines will trap the impurity away from the denuded zone. Okay, that is Gatoring, and that is very important factor. Yes. Say this is your material, and inside it is growing, basically it is the bulk crystal growth. So, you control the oxygen in such a manner, not very high oxygen is required. If you control the oxygen in such a manner that it becomes supersaturated at some point, so it will grow, basically the growth of the oxygen bubble say will be there. So, after some point, because of thermodynamic consideration, it will give rise to stress. So, the stress will be relieved by forming the dislocation inside the material. Okay? At that point, that dislocation line will trap the impurity. So, the impurity are trapped in a very small region away from the surface or away from the denuded zone. Okay. This is very simple thing, and you can foresee if you see the crystal growth process or that type of manufacturing plant, when you after some time when you can see in some foreign laboratory or elsewhere, you will see that it is a common practice, standard practice, Gatoring of impurity. Since no foreign body is involved, because during crystal growth it is being done. So, that is why this is known as the intrinsic Gatoring. Extrinsic Gatoring means after crystal growth, if you gator something after crystal growth, then that is known as the extrinsic Gatoring. But since this is a part of the bulk crystal growth, so that is known as the intrinsic Gatoring. Okay. And remember that this impurity will be very, very small. How much? 1 ppb. What is ppb? ppb is parts per billion. That means 1 in 10 to the power 9. 1 in 10 to the power 9 parts per billion. That means it is practically 1 second in 32 years. 1 second in 32 years, it is parts per billion. Okay. Or say one drop in 250 chemical drum. You have seen the chemical drums. So, one drop of water in 250 chemical drums, the dilution is known as ppb level of dilution, very, very minute, very, very small, 1 in 10 to the power 9. If you have 10 to the power 9 say marbles of red color and one marble is there in green color, so what is the impurity? It is ppb level. It is the impurity is, in that case we shall say that it is ppb level. And what is ppm? Parts per million. It is 1 in 10 to the power 6. okay, it is 1 in 10 to the power 6. That means, it is almost 1 second in 11 and half hours. Suppose we have a clock, it is going fast or slow by 1 second in 11 and half hours. Then you can say that it is going slow or fast by ppm level. It is basically 1 drop of water in 50 liter tank, physical, if you can consider, right. So, today we have discussed about some aspects of bulk crystal growth, particularly the Sharansky's technique, and next day we shall start the float zone technique. Okay? Thank you.